All right, let's tackle neutralization reactions and titrations. So, first, a neutralization reaction, think about the word neutral. It just means when you add an acid and a base together, you're going to get something neutral. Because when you add an acid to a base, you make water and salt. So, for example, let's take a look at our hydrochloric acid and our sodium hydroxide. That's a double displacement reaction. So now the Na is with the Cl and the H is with the OH, so we made H2O. So every single time you add an acid to a base, you're going to make salt and water. So memorize that. All right, let's complete and balance a couple of these reactions together. So first one here, we've got H switching places with Ca. So now Ca, which has a +2 charge, is going to be with PO4, which has a -3 charge. So this is going to be Ca3, PO4, 2. And what else did we make? H is now with OH. It kind of gets confusing because you're like, wait, where did the 2 go? Where did the 3 go? But remember, that's all going to come out when we're actually balancing it. So now let's balance the equation. So I'm going to get a different color here. We've got Ca3. We've got PO4, 2. Now, how many hydrogens on the left side? 2 times 3, there's 6 there, plus another 3 times 2, there's another 6. That's 12 hydrogens. So you need a 6 in front of the H2O. And it's just a 1 out front there. Saved the easier one for second. Another double displacement reaction. Now K, which has a +1 charge, check your periodic table, is with the sulfate, which has a -2 charge. So that forms K2SO4, and guess what? HOH, H2O. Now we need to balance it. We've got K2, 2K, there's 2 H's plus another 2 H's. That makes 4 H's, so we need a 2 out front on that one as well. All right, ready to move on. What is a titration? This is a technique where you've got an unknown solution. So it could be an unknown molarity of acid or an unknown molarity of base. It works either way. And you add the opposite. So if you've got an unknown acid, you add some base that you know what it is and you know the concentration, and you basically keep adding till you hit a pH of 7. The amount of base that it took to get that overall solution to neutral tells you about what the concentration of the acid was. And vice versa. If you have a mystery base, just take the pH of it basically and keep adding acid until it hits a pH of 7. Then you'll know based on how much acid you needed to add what the concentration of that base was. So there's kind of a fun way to do it without having to take pH paper and check every second where the pH is. You can use an indicator that changes color at a pH of 7, like phenolphthalein turns from clear to pink if it's going from an acid to a base, or it goes from pink to clear if it's going from a basic solution and turning into an acid. So again, a titration is the process of adding a known amount of solution of a known concentration to determine the concentration of the other solution. You can add an acid to a base, or you can add a base to an acid. The equivalence point is that magic moment where the number of moles of hydrogen ions is the exact same as the number of moles of hydroxide ions. You can imagine why this would make sense, because if you have, let's say this one hydrogen represents 1 mole of hydrogens, and you've got 1 mole of hydroxides, guess what? That's pure water right there. Versus if you've got a solution that has more hydrogens than it does hydroxides, this is an acid. And if you've got a solution with more hydroxides than hydrogen ions, that's a base. So it says here, in other words, when you have the same mole ratio of reactants in a balanced equation, you've got the equivalence point. Okay, so let's figure out some ratios here. HCl plus NaOH. It's a 1-to-1 ratio of acid to base. But this is a little bit different. Check out this acid right here, H2SO4. For every 1 mole of H2SO4, you need double the amount of hydroxides. And that's because when you dissolve H2SO4 in solution, 1 mole's worth has double the amount of hydrogen ions that 1 mole's worth of NaOH has. So you need twice as many molecules of NaOH to really neutralize that acid. Okay, it can work the other way too. Let's say we've got 2 moles worth of hydrochloric acid. That is going to perfectly cancel out 1 mole's worth of CaOH2 because there's 2 hydroxides for every 1 mole's worth of that molecule. All right, let's do some practice. How many moles of HCl will it take to neutralize 6 moles of NaOH? Well, we can do this a couple ways. Let's say each of my hydroxides is representing 1 mole. 1, 2, 3, 4, 5, 6. How many hydrochloric acids is it going to take to cancel those out? It's going to take 6 moles worth because it's a 1-to-1 ratio. Okay, let's do something a little bit more difficult here. Okay, how about this one? How many moles of hydrogen chloride, hydrochloric acid, would it take to neutralize 6 moles of CaOH2? Interesting. So 6 moles, 1 mole of calcium hydroxide is going to produce 2 hydroxides. So if I've got 6 moles worth, I'm going to draw these all out, even though this is a lot of work for this question and there's an easier way. It's nice to have a visual when you're first learning. So 6 moles worth of calcium hydroxides is going to give you 12 hydroxides. So 1 mole's worth of hydrochloric acid is just going to give you 1 hydrogen ion. So you're actually going to need 12 moles of hydrochloric acid molecules to neutralize those 6 moles of calcium hydroxide. Okay, and then what about this? 6 moles of H2SO4. Okay, let's do this the easier way. Start by writing what you know. 6 moles of H2SO4. For every 1 mole of H2SO4, you need double 2 moles worth of NaOH. See, because the NaOH only has 1 hydroxide in it, so you need twice as much. So the answer to this one is you'll need 12 moles of NaOH. Okay, a couple more. Let's write out the equation for this one. So we've got H3PO4 plus CaOH2. That's going to make Ca3PO42 plus water. This is not balanced, so let's balance it. We're going to need a 3 here, a 2 here, and a 6 here. I think we did this exact equation earlier. So if I want to neutralize 9 moles of CaOH2, how many moles of H3PO4 am I going to need? Well, let's use the mole-to-mole ratio. For every 3 moles of CaOH2, I need 2 moles of H3PO4. Notice 3 times 2, 6 hydroxides, 2 times 3, 6 hydrogen ions. That's why that's balancing out. But if I have 9 moles of CaOH2, I'm going to do 9 times 2 divided by 3. The answer is 6 moles of H3PO4. This makes sense. 6 times 3 is 18 hydrogen ions. To cancel out 9 times 2, 18 hydroxide ions. Okay, what if it's a weird number, like 6.4 moles of calcium hydroxide? Well, for every 3 moles of calcium hydroxide, you need 2 moles of H3PO4. So when it's a weird number like that, it's kind of handy. Multiply across the top, divide by the bottom. The answer is 4.3 moles of H3PO4 would cancel out that calcium hydroxide. All right. Couple harder problems here. What if we're not just talking about moles to moles? Because that's not very realistic. We're going to be given concentrations of solutions and amounts in liters, things like that. So let's do a series of questions here. Let's balance the equation first. Again, this is a repeat. We need a 3 there, a 2 there, a 6 there. That becomes a 1. First question, how many moles of CaOH2 will it take to neutralize 3 moles of H3PO4? Always start by writing what you know. Well, for every 2 moles of H3PO4, you need 3 moles of CaOH2. 3 to 2 ratio. 3 times 3 divided by 2, that is going to be 4.5 moles of calcium hydroxide. That's how many moles you need to cancel out those 3 moles of H3. And it makes sense, right? 3 times 3 is 9. We're canceling out 9 H's. So we need 4.5 moles of the calcium hydroxide. 4.5 times 2, that will cancel out those 9 hydrogen ions. All right. How about this question? How many liters of 1.5 moles of calcium hydroxide will it take to neutralize 1.2 moles of H3PO4? Start by writing what you know. We want to neutralize 1.2 moles of H3PO4. Let's figure out how many calcium hydroxides that's going to take. For every 3 moles of calcium hydroxide, we need 2 moles of H3PO4. So 1.2 times 2. Oops, I did this wrong. I set it up wrong. You got to make sure your units cancel out. Let's try this one more time. Sorry, you were probably going, what the heck is she doing? For every 2 moles of H3PO4, this is making more sense. You need 3 moles of CaOH2. So this cancels out. 1.2 times 3 divided by 2 is 1.8 moles of calcium hydroxide. That's how many will neutralize that 1.2 moles of H3PO4. Okay, now think back to your little molarity triangle here. Molarity, moles, liters. If we want to know liters, we're going to take moles divided by the molarity. So 1.8 moles divided by 1.5 moles per liter. Liters is going to flip up to the top. The answer is 1.2 liters of that solution will neutralize that acid. Let's do another one that I don't mess up on. All right. This time it says, how many liters of a 2.9 molar solution of acid will it take to neutralize 300 milliliters of a 0.7 molar solution of calcium hydroxide? Well, let's figure out how many moles of calcium hydroxide we've got to neutralize. So remember our little chart here. Molarity times liters gives you the number of moles. So we've got 0.7 molar solution times 300 divided by 3 is 0.3 liters. We're trying to neutralize 0.21 moles of calcium hydroxide. So 0.21 moles of calcium hydroxide, and we know for every 3 moles of calcium hydroxide, you only need 2 moles of H3PO4 to cancel that out. So that comes out to be 0.14 moles of H3PO4. Now, remember from the last question, moles divided by molarity gives you liters. 0.14 moles divided by its molarity, 2.9 moles per liter. We would need 0.05 liters of H3PO4 to neutralize that calcium hydroxide. Okay? Endpoint. This is the point where the indicator changes color. So remember, there's the equivalence point where you've got the exact number of hydrogen ions equaling the number of hydroxide ions. And the end point is a little bit past that because you've had to add a little extra base, for example, to get it to turn pink. Just a couple drops, but still, it's a little bit different. What did one titration say to the other? Let's meet at the end point. You still get chemistry CAD in these notes too. So when you're titrating an acid, for example, you're adding base. Here's a picture of what the equivalence point looks like. You're at a pH of maybe 1, you're adding base, adding base, adding base, boom! You get this curve here because this is a logarithmic relationship. And the phenolphthalein really changes at a pH of like 8.3, but that doesn't matter because this goes up so dramatically at that equivalence point. So one drop is a very small error. So when we actually do titrations in class, you'll see you go very slowly toward the end. Okay, there's another one. Dropping the base. So when you're doing a titration, there's a method to the madness because it can get a little overwhelming at first. Step 1, always write the balanced equation. Just like we've been practicing, acid plus base makes a salt. You'll need to crisscross the charges, and it makes water. Then, this is my own little trick. Write down your information, and I'll show you this in a second, underneath the chemical equation. Whichever chemical you know more about, like you know the concentration and how much you have, that's your known. Figure out how many moles of your known you're trying to neutralize. Then use the mole-to-mole ratio based on that balanced equation to figure out how many moles of your unknown you have. And finally, based on how much you needed to add, do molarity divided by liters to get that concentration. Okay, let's just do a thinking one here first. Oops, go back a slide. Let's say you added 200 milliliters of a 1 molar base to 200 milliliters of an acid, and that's when it turned pink. What must the concentration of the acid be? Well, it must be 1 molar because you added equal amounts, and it's a 1-to-1 ratio. Oops, I meant to circle the H there. How about this one? What if you had to add 400 milliliters of 1 molar base to 200 milliliters of the acid before it turned pink? What molarity must the acid have? Well, you had to add twice as much base. So that acid must have a 2 molar concentration. It must be double the concentration. All right, so let's do a titration. This one is made a little easier because the equation's already balanced for you. Okay, but let's say you've got a 25 milliliter solution and it's neutralized by 18 milliliters of this 1 molar solution of base. I'm just going to make sure I have enough battery here and keep going. All right, so first thing we're going to do is we're going to write the information below of what we know. So what I mean by that is, and also change it to liters. That's a little side tip. Change it to liters right away. We've got 0.025 liter solution of HCl. Okay? We've got 0.018 liters of this base, and it has a concentration of 1 molar. The mystery here is we don't know the concentration of the acid, but we know how much base we had to add. So we can do some math here and figure out what that mystery concentration is. So first thing, whichever the one is that you know 2 about, do molarity times liters to get moles. We are neutralizing, we had to add 0.018 moles of NaOH to neutralize this acid. And it's a 1-to-1 ratio. For every 1 mole of NaOH, it neutralizes 1 mole of HCl. So that must mean in this solution here that we started with, there are 0.018 moles of hydrochloric acid. Divide by how much you had to figure out the concentration of that acid. So the answer here is 0.72 molar acid. Now for this next one, in class I'm actually doing a titration. Okay, so I'm going to have to make up the data here, but we'll make it make sense, somewhat sense, but it's a mystery to me too. So we've got a base, we've got an acid, we know the molarity of the base, and we know the amount of my mystery acid in the flask. Okay? We just don't know its concentration. We know we've got 15 milliliters of it though. Above it, in something called a burette, we're carefully adding this 0.2 molar base. And burettes read backwards. So let's say the initial burette reading is 2.31 milliliters. Okay? The final reading's actually larger, again, because they read from 0 down to 50. So let's say the final reading is 17.81 milliliters. Trying to make my math somewhat easy here. So we're going to do a subtraction. 17.81 minus 2.31, that comes out to be 15.5 milliliters. That is the magic number of how much base we needed to add to neutralize that acid. So now we need to do some math here. Okay, so I'm going to rewrite the equation. We had HCl plus NaOH. We know that when I add those two together, I'm making salt water. So I had to add 0.0155 liters of the 0.2 molar base to neutralize the 0.015 liters of this mystery concentration. So write all your information first. Then you always do molarity times liters to get your moles of the known that you added. So in this situation, I added 0.0031 moles of sodium hydroxide. It's a 1-to-1 ratio again. For every 1 mole of sodium hydroxide, I know that there's 1 mole of hydrochloric acid molecules in there. So that comes out to be 0.0031 moles of HCl. Originally that was in that, oops, that disappeared for some reason, 0.015 liters of solution. So divide by 0.015 liters. This comes out to be 0.21 molar hydrochloric acid. I didn't really think about this, but yeah, they're almost identical because you added equal amounts almost, 0.015, 0.0155. So it makes sense that the hydrochloric acid pretty much has the same concentration as the base. Then there's 2 more questions in the notes. I'm not writing these out, but let's go through these together, talk through them. Here's another similar one. You've got the same reaction, and so underneath you would write 0.015 liters under the HCl, and its molarity 1.5 molar. And under the base you would write 0.0108 liters. First step, you do the liters times the molarity to tell you how many moles of hydrochloric acid you had to add to neutralize that base. It's a 1-to-1 ratio, so that means there were 0.0225 moles of sodium hydroxide in that mystery flask. Finally, take how many moles of your mystery solution divide it by how many liters you had. Now you know the concentration. It's the same steps every time. So when people struggle with titrations at first, the best thing to do is keep practicing, looking at examples. Over and over, it's the same technique. And then as you keep going, try not to be a robot. Try to actually understand what's going on. Okay, last one here, finally a little something different than a 1-to-1 ratio. It's a 1-to-2 ratio. It says you've got 0.2 liters of sodium hydroxide. So you would write that underneath the NaOH with a question mark of the molarity under the NaOH. But you know you needed to add 0.075 liters of a 1.25 molar solution of that acid. So you would write those two numbers under the acid. Multiply those together, we are neutralizing 0.094 moles of H2SO4 with that mystery NaOH. What's interesting here is there's only, for every 1 mole of H2SO4, there must be 2 moles of NaOH to cancel that out. So we've got to double that number of moles. And finally, divide by how much you had. The unknown concentration of NaOH is 0.94 moles per liter. Titrations in the real world. If you're thinking to yourself, what the heck, why do I need to know all of this? You should know that titrations are a very common procedure to figure out concentrations of things in urine and in blood. Pharmacists use titrations when they're developing new pharmaceutical drugs. Titrations can also be used to determine how much of a chemical is in food, like the fat content, the water content, the concentration of different vitamins. Titrations are also used to tell if cheeses and wines have aged enough. And then you'll understand this once we do the lab. Normal person, wow, what a pretty pink color. Me, crap, over-titrated with phenolphthalein indicator. All right, that is it. Good luck with all your practicing.